we need to finish our discussion here on bonding, focusing on metallic bonding, because we've looked at covalent and ionic, and in a lot of ways, covalent and ionic bonding, although different, they're kind of based on the same principle about gaining an octet and either transferring or sharing electrons, but again, really just trying to maintain an octet. So in some ways, they're very similar. And when we look at the difference in electron activities, we see that really it is a spectrum, that the bigger the difference in electronegativity, the more ionic the bond is. Well, metallic bonding is completely different. What metallic bonding is when we think about metallic bonding, these are metal atoms of the same element. So these could be, say, copper, they could be gold, they could be sodium, they could be anything to the left of the zigzag line. So if I have my little periodic table here, if I take my zigzag line, really all of our metals, when they bond to themselves, when we have solid copper, solid sodium, potassium, magnesium, anything, this is how it's bonding to itself. So how metal atoms bond to themselves is they bond to themselves through delocalizing their electrons. So their outermost electrons really are, we think about them as being delocalized or a little bit freer than our standard electrons in ionic or covalent bonding. So when we talk about metallic bonding, we often talk about positive metal ions in a sea of delocalized electrons. So not all of their electrons are delocalized, but again, their outside electrons are delocalized, which means they move freely among the positive ions. They're kind of, shared isn't the right word because they're not exactly shared, but they are delocalized, so they move a little bit freer. And this is the basis of a lot of the properties that we see with metals. So when we have these positive metal ions with these free electrons roaming around outside of them, again, like we said, this is what gives rise to the various properties of metals. So when we think about the properties of metals, what we've talked about before is that metals have luster, metals are malleable, metals are ductile, metals conduct heat and electricity, and we'll look at each of these and how this type of structure enables all of these properties to occur. And these are properties that all metals have. All metals conduct heat and electricity. All metals have luster. We have to be a little bit careful saying all metals are malleable or ductile because there is mercury, which is a liquid metal at room temperature, so it doesn't necessarily, it's hard to talk about a liquid as being malleable or ductile, but they all conduct heat and electricity. They all have luster. So why? So like we said, there's the sea of electrons. So metal atoms contribute their valence electrons kind of to each other. So those electrons, again, the key word is they're delocalized and they're free to move about. So they're not attached to any single nucleus. So let's think about our properties then. So B is an illustration here of electrical conductivity. So again, remember what electrical conductivity is a flow of electrons. Well, to have our ionic substances conduct electricity, we needed to melt them down or dissolve them in water. Metals, we don't need to do that. Solid metals can conduct electricity because of those delocalized electrons. So if we look at this, if there's all these delocalized electrons around, well, if we apply a charge to it, if we put in a flow of electrons, well, there's a path to move through because there's already electrons there. Kind of a similar thing happens with heat. Heat is really just motion, and if these things aren't locked in place really hard like an ionic substance, if they're a little bit more free to move because of the delocalized nature, then it can transfer heat really well as well. So ionic compounds aren't really good at transferring heat. Metal compounds are, because because temperature is really energy or motion. It's moving stuff. So to warm up this metal ion, we just have to get it to wiggle around a little bit more. And it can wiggle more than, say, an ionic substance because it's not locked in that one place. Now, metals do have a structure. They are solids. They do have kind of a lattice, but these metallic lattices just are not as rigid as our ionic lattices due to their nature of how they bond, doing the merging of their electron clouds. And so, again, if we apply a pressure to them, if we push on them, if we test their malleability, so this would be a test of substances' malleability, what happens is the positive ions can move out of the way because they can shift on that sea of delocalized electrons. So it allows metals to be malleable, which means we can form them, we can pound them into sheets, we can roll them into pipes. So there's lots of things we can do with metals due to, again, the nature of these delocalized electrons. So another thing we see with metals, and here's some samples of metals. This is, up here, this is magnesium, which is an alkali earth metal. This is obviously copper right here. And we have, actually I believe this is some tin on this dish right here. So we have some different metals, and again, one thing we'll notice about all of them is notice how they're all flat. Well, besides the tin here, they've all been pounded into sheets. They're all malleable. And one thing we can actually say about metals is most metals are actually too malleable to be of any functional use. Now, if we have pure copper is going to be a great conductor of electricity and heat, but one problem that pure copper might have is it's too soft. So you cannot actually wear, say, pure gold jewelry because it's much too soft. It would kind of fall apart. You'd probably ruin it or dent it or damage it really easily if it was pure gold. So actually a lot of our metals, because they are so malleable and they are so bendy, when they're actually made into products, they're made into alloys. Now these are just some couple images of alloys, but what alloys are one metal. So perhaps this is steel. What steel is it's not iron. Iron is not steel. Iron is the main component of steel, but what iron has in it is it has atoms of actual carbon. So when carbon gets into that metal lattice, now when you would try to apply a force to it, so if I try to apply a force, hit it with this hammer, now these don't move quite as easily because those other alloys, the other things that are in there, kind of mess up the lattice a little bit. So if we have a nice metal lattice like here, all these layers can freely move on each other, or not super freely, but they can be bent and pushed. As soon as we put in these alloys, these other metal atoms in there, it kind of messes up that metallic lattice, and now it reduces the malleability of that metal. Now, why would we want to reduce the malleability of the metal? Well, it makes it stronger, it can make it harder, and so these are good properties of metals. So sometimes metals are too malleable, or too ductile, they're too soft to be of any practical use. Just like iron is too soft as pure iron to use as a construction material. But steel, now, that's a stronger substance. So a lot of times when they talk about alloys, the reason we have the alloys is to make those pure metals, which are very soft, malleable metals, stronger. Another thing that our mobile outside electrons give rise to is the lustrous quality of metals. So all metals have luster. So what's happening with metals is that when light hits them, instead of being absorbed like a lot of different materials, what happens is that light is reflected due to that nature of those mobile electrons on the outside. So every property we know about metals has to do with having these electrons that are mobile, that there's this delocalized electrons that bond things together. So that allows for these metals to transmit electricity, to transmit heat, to be malleable, to be ductile, but also to be lustrous because light hits it, and these mobile electrons are free to reflect that light really easily. And one thing we want to think of is, again, we're talking about all the metals on the periodic table. So if we have our zigzag line drawn here, all of these are going to exhibit that similar behavior. Now, one thing we might want to look at is the difference in their bonding strengths, or also their reactivity. If we look at our metals, what we know is our alkali metals are all very reactive. They will react with water violently. They'll react and corrode with air. Now, all of our metals are going to react with air, or for the mass majority are going to react with air. They're going to oxidize. They're going to rust. But these will react with water. Even calcium, magnesium are going to react with water, not quite as violently, but they will react with acids. If we go further over in the periodic table, notice what's here. Look, we have copper, silver, gold, platinum, and palladium are right here. So these are what we consider more precious metals. So these are precious metals. One reason we call them precious metals is these are generally unreactive metals. So they're unreactive. on this side of the periodic table. On the opposite side, these are our more reactive metals, with kind of metals with reactivity in the middle here. So our general trend of reactivity for our metals is things on this side, gold, silver, platinum. These are generally unreactive. The things on the other side are more reactive. Now, what does it mean if these are unreactive? Well, two things it means. One, things that are unreactive have more mobile electrons, and so the bonds between them are stronger. So as we add d shells going down, really there's more mobile or more potential for mobile electrons, and so things bond together a little bit tighter. When they bond together tighter, they're not as willing to give away their electrons, their valence electrons, like we might see with our alkali or our alkali earth metals. So here's a chart of that reactivity. So notice potassium, sodium, calcium, magnesium, even aluminum are some of our most reactive metals. On the very bottom of our reactivity list, we have copper, silver, gold, platinum. So again, things on that far right side of our metals are generally unreactive. Things to the far left generally are very reactive. And so the least reactive ones have stronger bonds because they have more delocalized electrons holding things together. Our most reactive ones are ones, again, on the opposite side. So another thing we might remember about our metals is that they can form multiple oxidation states. So here's some. Notice iron can form a +2 or +3 ion. Copper can form a +1 or a +2. So there's a lot of metal ions that have multiple oxidation states. But notice they're not losing all their d electrons. So they're not forming ions that are, +1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. They're not forming +11 ions. So what we might want to look at is what electrons are they losing when they're forming these ions and why? So what we should think of when we look at metals and we're trying to predict what their charge or oxidation number is going to be is they have to lose their outside electrons just like anything else. The only difference is they have this d shell. So which electrons they lose and how many is a little bit different than our main group elements where we can easily predict 1, 2, 3, 4, 5, 6, 7. We know how many valence electrons they have. They're trying to get to an octet. Transition metals are a little different. If we take a look at, say, titanium is right here. Notice its electron configuration and its noble gas configuration. When it forms an ion, what it actually does is it loses its 4s electrons first. So these electrons leave first, even though they also fill first. So this is kind of the difficult thing. And then it also loses these two. So the most common charge on titanium actually is a +4. So that's true for titanium. It loses all of these electrons. But that's not true for something like vanadium. Vanadium does not lose all of its electrons. Well, I shouldn't say that. It can, but it's not maybe its most common oxidation state. So vanadium can form a +2 because it can lose just its 4s electrons. So you'll notice that most of our metals can form +2 ions because they lose those 4s electrons. So vanadium can be a +2 because it can lose those 2. Vanadium also can actually be a +5 because it can lose those 2 and its d orbitals. So there's a lot of different options for these. If we look at chromium, again, the most likely thing for chromium to do is to take this one 4s electron and lose it. But it also can lose all of its d shell. So it, again, has a couple different oxidation states or charges that it can have. Manganese being the same. Manganese can be a +2, manganese can be a +7. There's a couple other options in between that. Manganese can be a +4, I believe. Iron, notice the two most common for iron are iron can be a +2, where it loses its 2 4s, so it would be iron +2. But iron also can be a +3 fairly commonly, where it'll lose these 2 4s electrons and one of here, then it'll still have a d shell, so it'll still be relatively stable because it'll have a half-full d shell. So those are very common charges for iron. And we do have a couple of our transition elements that actually only have one oxidation state. Zinc only loses these two. This full d shell does not break up. It is too stable, it does not break up. So zinc is only always a +2. That's the only oxidation state or charge that zinc can have. Scandium is similar. Scandium loses all of these, and scandium is primarily a +3 and really does not form other oxidation states. So those are two that are kind of different. Sometimes they're actually not considered transition metals. Transition metals sometimes are defined as having a partially full d shell. So these transition metal ions have to have a partially full D shell. If they don't, if it's either empty or it's all the way full, then sometimes they aren't really considered full transition metals. So let's summarize some of the properties that we've talked about with our bonding thus far. So if we look at hardness and malleability, so our metallic compounds, which are giant metallic compounds because they are still lattice structures, they're just not rigid lattice structures like ionic compounds. They're hard, but they're malleable rather than brittle. Ionic are going to be brittle, hard, but also brittle. If we look at their melting and boiling points, is very variable for metals, but most are generally high. Now there's exceptions, obviously, like mercury's the big exception that has actually a lower melting point, but generally metals have strong bonds and have really high melting points. Ionic almost always have high melting points here. Now here's the difference as well: electrical and thermal conductivity. Metallic compounds can conduct electricity as solids and as liquids. Remember, ionic cannot as solids, but they do when we melt them down, when they're liquids, or if we dissolve them in water. So ionic compounds have to dissolve in water. Metal compounds do not dissolve in water. Again, almost as a rule. So examples of things that are metals are iron, copper, lead, mercury, but even alloys like brass have giant metallic structures. Ionic, we have sodium chloride, calcium oxide. Now, we have a couple other things. If we look on the other side, again, covalent are very different. If we look at molecular covalent compounds, or just covalent compounds, typically they're soft and malleable. They have low melting points, low boiling points. They're typically liquids or gases, whereas ionic and metals are almost all solids. Covalent compounds are almost always liquids or gases. They never conduct electricity in any state. Mostly they're soluble in things that are non-polar, so they're not very soluble in water. Mostly they're soluble in non-polar stuff. These are things like carbon dioxide, like ethanol, like iodine. So one that we haven't really looked at is giant covalent structures. And there's not a ton of giant covalent structures, but there are some covalent structures that form giant lattice structures that are similar to ionic compounds, but again, they're covalently bonded. Now, these things do have some covalent properties, whereas they don't conduct electricity for the most part. They're insoluble, again, for the most part. But because they're big repeating lattices, they tend to be very hard, and they tend to have very high melting points. Now, our main examples of gigantic covalent structures are things like diamond, formed by carbon, graphite, also sand, silicon dioxide. So let's just look at those structures quick as an example. So notice here's some allotropes of carbon. So these are all carbons, so they're all forming covalent bonds. But the thing about them is they're massive. They're massive repeating structures, just like ionic compounds. Again, not just like ionic compounds, because there's no electrostatic charge. They are all sharing electrons. But because they are so big in a repeating structure, they also have the high melting points, and they're very hard and strong, like ionic compounds. This is our other example of a giant covalent structure would be silicon dioxide, which is the primary component in sand, but again, also a giant covalent structure where it's going to have a very high melting point. Again, all sharing of electrons, but high melting points like we might see with ionic compounds.